In this video, we're going to look at potential functions. But first, we're going to do just take a minute to do just a little bit of background. So suppose we want to evaluate say this, which again, that would be like work over some curve C. Or let's suppose we wanted to evaluate this over some curve C. And suppose we can find the function suppose we can find a function f such that the gradient of f will give us our vector field f. Then we can use the fundamental theorem of line integrals. So in other words, if we can find this function f, and whether you have to do this or this, remember, these two are equal to each other. And so let's suppose you wanted to find this, and then you have this potential function, and that's what we call this small f here, a potential function. We can say that this would be equal to this, and then recall that if we have an integral of this form, we can use the fundamental theorem of line integrals, which says you can evaluate the function at, say, the endpoint minus the starting point. And that's kind of our goal. So we would like to find a potential function, that is a function such that if we take the gradient of it, we'll get our vector field, and then we can use the fundamental theorem of line integrals to evaluate our integral. So let's take a look at this. Let's do an example. Do an example here. So let's say find this integral f dot dr. And once again, even if we're asked to find the, say, this one here, f dot t ds, we would use the same process over a curve C, where C is given by, and our C is given parametrically by this equation. So we want to find this integral, and where f our vector field is given by 3y squared plus 4 cos x 6xy plus 3ey. So let's do this. Now, the first thing we should check is to be sure that we have the potential function available. Not all vector fields came from potential functions. So check first of all to see if we have a potential function. Check to be sure we have this for this vector field F. And we do that by looking at our vector field here, and we're going to set this first element equal to P, and set the second element equal to Q. So I'm going to call this 3y squared plus 4 cos x 6xy plus 3ey. So again, all I did was call this P and this Q. And then our test is we're going to take the partial derivative of P with respect to y, almost opposite what you'd think because it's in the x position, but we take the derivative with respect to y of this, and we do this, we get 6y. Over here, we take the derivative of q with respect to x, and we also get 6y. Because, of course, over here, since this is with respect to y, this will disappear. This has no y's in it. And this is with respect to x. This will disappear because there's no x's in here. And now, since since we have dp dy equal to dq dx, that tells us that a potential function f exists. That is, it exists for this vector field. So now we can go ahead and find our potential function. So now, again, remember what we want to do. So finding the potential function. So remember what we want to do. We want to find a gradient of f that's equal to f. And now let's write down what those mean. Of course, the gradient of f is going to be a df dx df dy. That's just the definition of a gradient when you have two variables, which we have here. And f in our case was given by this. And so that's going to be 3y squared plus 4 cos. I'm just writing our vector field f down over here, the one that we're given in the problem. Like this. And then so let's just match these up. So what does this say? This say we want to have a function f such that its derivative with respect to x is equal to this, and its derivative with respect to y is equal to this. So we want df dx to be equal to 3y squared plus 4 cos x, and we want df dy to be equal to 6y plus 3ey. And now now you can start with either side. You can start either over here or over here. That's up to you. I usually just out of habit start with this side where we have x. And so since, again, we're looking for this function small f, so we know its derivative with respect to x is this. So let's go backwards. Let's integrate this. So I want to integrate df dx with respect to x. And in other words, we're going to integrate this with respect to x. And when we do this, so if we integrate this with respect to x, we'll get 3y squared x. And integrate this with respect to x, that'll be 4 sine x. And then usually we put, anytime we integrate, we would put plus c. But actually this time though, we're going to be, you could not only have a constant here, you could have a function of y here, right? Because we're integrating with respect to x. So if you think of going the other direction, taking the derivative and going this way, any function of y will disappear when we take the derivative with respect to x. So this could not only be constant, but could also possibly be any function of y. And this would mean this would be a function of y, could be constant and or have the variable y in it. So now this is the function we're going to kind of be building on. So again, remember, that's what we want to find is our potential function f. So it's going to look like this. We just have to fill in some details. And so you might want to, it's up to you. You might want to give this a name. A lot of times I just call it like equation 1 or equation star. So now we want to use this information over here. We have df dy over here. We know what that is. So we can probably find out what our gy here is if we can somehow use this information. So this is df dy. So let's take the derivative of this with respect to y. And this is when we take the derivative of this with respect to y, this is going to give us 6 yes, 6 yx. And then this is going to go away. Plus g prime y. So all I did was take the derivative with respect to y here, because I want to match it up to what we have over here. So now let's set these equal. This is df dy. This is df dy. We can set these equal. So if we set these equal like this, and then notice this and this will cancel. So we have that g prime of y is going to be equal to 3ey. And then also we can say this is the derivative with respect to y. And so let's integrate this to find g. So if we integrate both sides with respect to y, and that'll give us g of y is 3 ey, like that. And then plus c. And then finally, put this back up here into equation 1. And when we do that, we get f y squared x plus 4 sine x plus 3 ey plus c, like that. And that's our potential function. Now we can use that along with the fundamental theorem of line integrals to say, so let's go back and see what we actually have. We originally wanted to find our f dot dr. Sorry. We wanted to find f dot dr like this, but we found this potential function, and that potential function, we take the gradient of it. We found it in such a way that if we take the gradient of it, we get f, and you could double check that. It wouldn't hurt to take time to double check it. Take the gradient of this, you'll end up getting our vector field that we started with is this. That was kind of the goal of the potential function. So in other words, so we found this potential function like this. And then by the fundamental theorem of line integrals, we said that if you have the gradient of a function, that's going to be and you have like a line integral, that's going to be equal to the endpoint minus the initial point. I should say the function evaluated at the end of the initial point. So the last thing that we have to do now, we were given our r of t. It's r of t squared plus 1 from 0 to 2. And we'll find the endpoints. Our beginning point was 0. We put 0 in here. That's going to give us 0. And 0 squared plus 1 is 1. If we put our endpoint 2 in, we're going from 0 to 2. That's going to give us 2. And 2 squared is 4, plus 1 is 5. Like this. And then, so now we can use our fundamental theorem. So let's just go back here. Again, you don't have to put all these steps in when you're doing these problems. We probably didn't have to write this out first. I just wanted to show where we were headed. And so we can say that this is equal to this. And then we want to put our endpoint of our potential function minus our starting point. That's going to be then our endpoint was this 2, 5. Our starting point was 0, 1. And go back to your potential function, which is this right here, and put in these values. Put in 2, 5 for x. It's going to be 2 for x, 5 for y. So let's do that. So that was putting 2, 5 into our function. Just double check, be sure I did everything correctly. That looks correct. Then subtract the 0, 1. This is going to be 3, 1 squared times 0. That's going to go away. Plus 4 sine 0. Plus 3 e to the first. Oh, by the way, I knew that we had bounds, so I knew our constants were going to disappear. But if that makes you a little uncomfortable, let me put the constants in there. But you can see they're going to cancel out. So I put the beginning point. We get 0, 4, 0, 3 e to the 1. And then this is going to be, that'll be what, 25 times 2 is 50, times 3 is 150, minus 4 sine of 2. I'm going to need my calculator to do that, or you can just leave it in that form, plus 3 e to the 5th. And this is going to be 0 here. This is going to be 0. Like I say, the c's are going to cancel. And then, so it's going to be minus 0 plus 0 plus e to the 1st. And so you could leave it in that form or put it into your calculator to get an exact answer. And we could maybe, even before you put it in the calculator, you could simplify it just a bit. Again, so for the sine, we would be assuming we're using radians. So that'd be our final answer. So we're going to now take a look at this example. So we want to find this integral here, where C, the curve, is given by this parameterization, and T is from 4 to 9. And this is our vector field. So let's take a look at this. Once again, we want to check to be sure that we have a potential function. If we do, once again, we can use the fundamental theorem of line integrals to evaluate our function. So again, remember that this is P. This is Q. Remember, to see if we have a potential function, we have to do dp dy and see if that's going to be equal to dq dx, dp dy. So when we take the derivative dp dy, we'll bring this forward. This will be 3 halves 16 x cubed y, subtract 1 to be a half, plus 0 plus 0. And let's see, this will cancel, be 8, this is going to be 24. X cubed y to the 1/2, like this. And then over here, dq dx is going to be 24 x cubed y to the 1/2 plus 0. That's going to go away. So these are equal. dq dx is equal to dp dy. So a potential function exists. Let's go through and find it. Remember what we want. We want something where we take the gradient will be equal to our vector field. And in our case, our vector field is this. And I'm just rewriting it like with the angle brackets rather than the IJ notation. So we have this again. All that is our vector field. And we want df dx equal to this, df dy equal to this. That. And then to find our function f, like I said, you could work with this side and integrate this with respect to y, but I usually start over here just out of habit, but you can do it either way. So again, if we have df dx equal to this, we could find f by integrating this with respect to x. In other words, we're going to integrate this with respect to x. So we do that. Integrate this with respect to x. It'll give us a x to the 4th divided by 4. So it'll make this 4x to the 4th y to the 3/2. Integrate this with respect to that'll be x squared divided by 2. And that'll make it 2x squared. This will be 4x. And just like before, remember when we're integrating with respect to x, we could get a constant here or possibly a function of y. So we'll just put a general function y. Remember, this notation means this could have y's in it and or constants. And so this is going to be what we're going to be building on. And so now we want to find our g of y. So what we have to do, we have to use our information over here to find df dy. Take the derivative of this. This will be 3/2 times 4 x to the 4th, y to the 1/2. And that's going to go away. That's going to go away. And then over here, we'll have the derivative of our g. And actually, let's see, what's this going to be? Cancel here. That's going to be a 2 times, that will actually be 6. Let me replace that with 6. Like that. And then we want to set these equal, because we're going to try to find this g of y. So let's set this equal. This, again, we can do this because this is df of y. This is df dy. So we can set those equal. And notice that this and this are exactly the same. So when we're working with this, those could cancel. Then we have g prime of y equal minus sine y. Then to find g, of course, just integrate this. And when we integrate that, let's see, that changes sine. We integrate sine, so I'll end up being like cosine of y, and then plus c. Now this time we're not going to have, we'll just have a plus c, because this was just functions of y only. So then finally put this into equation 1. And that's going to give us that. This is our potential function. Now we can use a fundamental theorem. And now to use a fundamental theorem, we're going to need our endpoints. And so let's see, let's go back to see what we had. We had r of t was equal to this. So let me just write that down so we have this in front of us. This here. And then our endpoints are at 4. And so it'll end up being 6. 6 will be the 1 point. Then 9. like that. Let's just double check my numbers. Again, all I did was put 4 into here and 4 into here and got 6 and 6, and put the other end point here. Oh, and I did make a mistake. This should be a 7 over here, shouldn't it? Like that. And again, put the 9 over here. 3 times 9, 27. Minus 6 gives us 21. So again, now use our fundamental theorem. And again, you don't have to write all this out, but just to remind us like what we have. We originally wanted this, which was equal to like our FDR. Like I say, you don't need to write all these steps out. But we found the potential function such that we took the gradient of it. We got our vector field. And so now then we can just use the fundamental theorem, which says we can take f at our endpoint, which was 9, minus our starting point, which is 4. Again, you don't have to put all these steps. I'm just kind of showing like all the steps. So if we put 9 in here, that was 7 and 21. And this was 6 and 6. Put this into our potential function. And recall what our potential function was here. This would be 4, and put a 7 here. And then y was 21. Plus 2, 7 squared, 4 times 7. Excuse me, 4, that should be 4 times 7. Cos 21 minus c. So let's just double check. So all I did was put our second point 721 into this function here like this. 7, 7, 21. And then do the same for our lower point, which was 6, 6. This was our initial point. By the way, these should both have been plus c's here at the end. And we get this. And I'll let you put that in your calculator and figure that out. But that's the way you would do it. That would be the integral. And once again, these c's will cancel. Then you can put the rest of this in your calculator. Again, you can, unless told otherwise, you can always assume that sine or cosine are going to be using radians. Let's take a look at this problem. I had to write down ahead of time just to be sure I wrote everything down correctly. And again, we have to evaluate this line integral, where C is a circle represented parametrically by 4 cos t, 4 sine t, t from 0 to 2 pi. And our vector field F is given by this. And again, we're wanting to use the fundamental theorem of line integrals to do this. So again, we have 2xy sine x, y x squared cos x, plus ey squared, x squared sine x, plus 2y ey squared x, cos t minus y sine y. And so, first of all, let's see if we have a potential function available. And again, I won't write this down again. Let me just note here that this is P and this is Q. So, and let me do the P dy. And let's take a look at that. That'd be the derivative of this thing with respect to y. Some of this is not too hard. This is just going to leave us with 2x sine x. Over here, this is going to be x squared cos x. Because we just had y's in each of this. And this will just be ey squared times the derivative of this. And that's going to be the derivative of that exponent, 2y ey squared, like this. And then dq dx, derivative of this with respect to x. So over here, we're going to have to use the product rule. The derivative of the first times the second plus the first times the derivative of the second. Again, if you do it in the other order, that's fine. In other words, you could take the derivative of this, you could take this times the derivative of sine plus the derivative of this times sine would be the same thing. And then let's go to the next term here. This has no x's in it. So, oh, yes, it does. That has an x here. So the derivative of this is going to be 2y ey squared. This is the one, no x's, no x's. So those are just 0. So notice these are the same. So we have dp dy equals dq dx. So potential function f exists. But notice one thing very important. Our curve C is a circle. And so we might be able to save ourselves some time here. So if you think about the fundamental theorem, again, it's going to be, we're starting with this up here in this case. And we've got some gradient here. And usually this is going to be equal by the fundamental theorem. Once we find our potential function, we can put our endpoint minus our starting point into our function, onto our potential function. But now, though, notice we have a circle. And so we're going to traverse this circle. So we're going to start and end at the same point. So that means, so this is going to be our endpoint A, but that's also our starting point A and our endpoint B. So that means these two are going to be equal. So, so once we have verified that we have a potential function, we really don't even need to find the potential function, because if we evaluate our function at the endpoint minus the evaluation of function at the final point, it's going to be 0 on a closed curve because these two are going to be the same. So this is going to be the same. So our answer is going to be 0. Again, this would only be true only in a closed, smooth curve where you're starting and ending at the same point. We're traversing a circle, so we're going to start at the same point as we're ending. So this is going to be 0. Again, though, the important thing, though, we had to verify that we had this potential function. If the potential function did not exist, then we could not apply the fundamental theorem of line integrals, and we could have not come up with this as 0. But because we had a potential function, we knew it's out there somewhere. We really don't have to find it in this case because we're starting and ending at the same point, so our integral must be 0.